We're looking at mountains this week, and to begin with, we're thinking about cable cars. And so we've imagined a cable car network that is on this mountain. And the way that it's going to work is that we've got lots of stations, but the way the cable cars work in this case is that they sell triangular trips. So you kind of can go to 2 stations and back. And they're wondering how many different trips are possible on this network. So let's just have a look at how that might work. For example, we'd get a trip that went to this station, and then back. For example, that would be one trip. I'll change colour. And we might have another trip that started at the top maybe. So you can start wherever you like, and maybe goes down there, and back up. So they always kind of visit 2 stations and go back to the start. And so we're wondering how many different trips would be possible on this mountain. So let's take this last triangle that we started. It wouldn't matter where you started on that triangle. You could start anywhere you wanted, and but it would be the same ticket that you would get. So how many different triangles would there be that you could go to? So as long as it's a set of 3 different stations, you'd have a different triangle. So that's how that challenge works. Now, another way to think about this activity is we want to design our cable car network. And we're going to do that by, I could, for example, draw a triangular trip. That would be one triangular trip, let's say, and then I might draw another one which is to here. I can add a station, so anywhere I join up to things, I could just add a station there. I'll just draw a little thing for that maybe, and then let me do a third one. And so this is my 3rd triangle, but as you can see, that has actually allowed now, just by putting those cables in, that's allowed many other triangular trips, or a few other triangular trips anyway. I think we found 7 different triangles that you could find out of this. So just from drawing 3 triangles, actually there are 7 triangles there if we spot hidden triangles. So what we want to see if you can do is, can you construct a network, and we want you to connect all of the points up in such a way that they produce triangles. So they produce triangles. Actually, I'll just get rid of this one, let's say. But we want exactly 10 stations, no more, no less. And yeah, sorry, exactly 10 triangles, not stations. Exactly 10 triangles. So you can see from what I've made, there's one triangle here, let's say, but then there's also a triangle which counts for both of, that spans that space, if you like. If I just do it with a slightly different color, we can see that actually we've got another triangle which goes from here and goes this way. So it's a slightly bigger triangle, and we can kind of call them hidden triangles because they're kind of hiding, made up of other shapes in the thing. So it looks like I've probably got more than 10 triangles here. So that's what we're looking out for. You can actually just trek up a mountain. So the only thing is, of course, you can't really walk up if it gets too steep. So usually paths on mountains try and limit the amount of steepness and take you up as gradually as possible. And so we're thinking about how we would make a path on this particular mountain if we wanted to get to the top. And we said that we want we can't walk up an angle of more than 10 degrees. So on bit paper, which is how I make these videos, they do have an angle tool on here, which you can kind of use. And so you can see that horizontal on this is 90, It's kind of like bearings. And so really we want to go a maximum of 80. That would be the steepest slope that we could do. So as you can see, that one, the point that's just on the right there is a bit too high, and so it would need too steep a path from that point. But this one over here is just about okay. Yes, we could just about do that. So that's a fine. So we could go to that path and that would be fine. And we can just draw that path in. Now you'll be using a protractor probably to measure this, which is fine too. And then from there, again, what we're going to look at, yeah, just about. Depends how strict we're being. Probably if we're being super strict, then no, we wouldn't be able to get to that one, because we started high up on the dot and so on. But yeah, let's imagine that that one might be okay, or I suppose we could go to this one at a push. We could get to that one, let's say. And that's the idea. We're just going to try and check out the different ways we could get to different spots on here and see if we can make our way up the mountain by that means. Now another puzzle that we are looking at is a shape puzzle. And the way this puzzle works is we've got to find shapes that have 3 points in common and see if we can decide what sequence they would go in. If we want a sequence such that each shape has 3 points in common with any shape that's next to it. And we want to put them in order so that happens. So for example, let's say if I started with this one, I need to find a shape that has 3 points in common. So I could put it on this, I can kind of put it over so that we can see it. But actually you'd kind of have to just observe or measure, I suppose. Measure some of the angles and measure some of the lengths. So yep, there we can see the top has the same kind of length and the right side has as well, so they match up. This one seems to match up with that one. Now another rule that I didn't write down was that really we want to alternate between quadrilaterals and triangles also. So we want our sequence to alternate between quadrilaterals and triangles. So that's the idea of it. Now on your sheet we can just number them, decide which ones we think go first and try it out. Let's say I think this one goes first. Okay, so that's number 1. Maybe this would be number 2. Maybe then this would be number 3, for example. Then but then I'm a bit stuck because I haven't got anything that this triangle won't match up with that number 3. So I'll have to find another way around for that. And yep, there's a slightly more tricky way to get from start to end there. But where this has all come from, or at least the idea that we're using here, is we're imagining that this is a climbing wall. So that's why we've used the shapes in the way that we've used them. And we can see that we start off with a shape which is a quadrilateral, and if you see, if I put it there, it's the same as, imagine I'm holding on to 4 points on the wall. Now if I'm climbing, I might want to, I'll need to move one of the points of contact to move it to another place. So for a moment I would have just 3 points of contact on the wall, and I'd need to find the shape that might do that. I think it's this shape, so let me check. So now I've got 3 points of contact on this wall, and I've lifted off, in that case it's one of my legs, my right leg has been lifted off, and that's going to try and find another hold. So where's the next hold, I might ask? Well, it's got to have 3 points in common with the same 3 points that I've been holding on to up till now. I think I see one over here. There, yes, that one works. Good. And you can see that I've got a new point that I've put my foot on over here, and now I'm ready to move another body part if I need to. And the goal is to see if we can get all of these 17 pieces into a sequence. And you can feel free to just number them, starting with 1. So that means we found a 2 over here. I'll just write 2 in. Let's say that one was 2, and so on. And then we find 3 and 4, all the way up to 17. They should be all in a sequence that correspond to the different moves. Climbing subtractions. And in this one, we've just got the 15 numbers. But let's start with, we're just going to imagine the first 6. And we want to put some numbers. So we're just dealing with the first 6 to start with. But the activity works in the same way when we use the other numbers. So just the first 6 for now. And what we're going to do is we're going to create, for example, if I put some of the numbers in here, let's say I put 6 there and 2 there, I get the difference between them. And now the difference between them is 4. And I'm not worried, sometimes if you do subtraction you get a negative number, but we're not worried about negative numbers. We're just going to have the positive, the positive number of whatever it is. Good, so that worked there, and then I might put a 5 there, let's say, get the difference of 3, and then that means that I can put a 1 in there because the difference between 4. And there you can see I've managed to get all the way up to the top starting from that level. But we can make it more difficult by adding in perhaps the numbers up to 10 and do the second row. So we could use the second row if we added the numbers up to 10 in, or use all the numbers and go all the way to 15. Alright, so that's another puzzle that we can do, and it's a tricky puzzle though. It is a tricky puzzle. So what we can find we might want to do is do some analysis on it, and we can do that by looking at how odd and even interact in this way. So what happens when we have odd or even? If we just look at whether the number's odd or even, and what the result will be. Because remember, in our puzzle we have 15 numbers, and 8 of them are odd and 7 of them are even. So that might be a way of kind of doing that. So if we had even, if we subtract an even number from an even number, we get an even number. And so we find that actually we end up with too many even numbers, because before long, look, we've already got 7, but that whole row is going to be even, and actually they're all going to be even. So that's not going to work. We can't have all even numbers at the bottom, or it will produce a mountain with all even numbers, and we haven't got all even numbers. All odd numbers is a similar problem, because we end up with all even numbers. When we subtract an odd from an odd, we end up with even numbers. So we get the similar problem, because everything from there on will be even. No good. So I'm just getting rid of those ones, but some of the others will probably be a little bit better, and that's what we're going to be looking for. This one, so odd and even, the difference between an odd and an even is going to be an odd number. So we start getting some odd numbers there and some even numbers, and then we can see how that builds up. Builds up with different kind of odds and evens and so on. So, but do we have, we need, the numbers that we're using have 7 odds, 7 evens and 8 odds, and so we need our, looks like we've got too many odds here. Yeah, so that's how this activity works, and that's how this analysis might help you. And just to note that actually this produces a pattern, because we've got 2 symbols. It ends up being a bit binary like, if we imagine them being as 1s and 0s, and it becomes being a bit binary like. And if we're looking at binary, it might be worth us also exploring with exploding dots. So that's what that page is about, and it's well worth looking at exploding dots for any level, even for younger children.